Come on and
Jumping is one of the more difficult mechanical movements. Although not as frequent in normal life, jumping is a very important technique for athletes. It is one of the primary tools to measure performance in sports, as jumping requires the use of many explosive muscles. Jumping requires a lot of energy input. The vertical leaps made by athletes on land are already dazzling, especially in the context of force required, as we will discuss shortly. However, we wanted to go one step further and analyze how impressive it is for these athletes to be capable of jumping out of a pool and just how much more difficult it is compared to a normal dry jump. First, we will take a look at an average dry jump and build up the difficulty step by step.
First, let us take a qualitative look at a normal vertical jump. The jumping begins with the preparation phase, where the flexion of the knees and hips occur. This is the crouching position. Then comes the takeoff phase, where there is extension of the knees and hips in order to straighten the body for takeoff. Then we enter into the airborne phase and then the landing phase. Most of the energy input during a jump occurs during the first two phases. The muscles used during a vertical jump are the gluteus maximus, semitendinosus, semimembranosus, the long head of the biceps femoris, the abductor magnus, and the quadriceps femoris.
Clearly, the motion of the jump out of a pool is a little more complex than the jump just demonstrated. There is a need to stick a landing. Therefore, let's consider the same person completing a 4-foot box jump. This models what the jump out of a 4-foot pool would entail without any water present. Most of the calculations are similar to that of the previous step. However, since the final landing position consists of the femur being parallel to the ground, we must account for this and measure the person's center of gravity to find the true height of the jump. With the following calculations, we are able to find the displacement of the feet from start to finish, the necessary initial velocity, and the necessary force required to produce that velocity.
The ledge height is 4 feet, or 1.219 meters. The group member's height is 6 foot 2, or 1.8796 meters. And from this we can determine the length of the femur using a generally accepted ratio of femur length being 27% of the body height. This gives us a value of 0.509 meters. Since the group member lands on the ledge with his legs at 90 degrees, the femur length is subtracted from the box height to determine the distance of the jump, which gives a value of 0.71 meters. To determine the initial velocity of the jump, we must first determine the time of a jump from launch to landing. Since we know the acceleration and distance, using the equation for distance shown, we found the time of the jump to be 0.3805 seconds. Using the known acceleration and now known time, we found the launch velocity to be 3.73 meters per second by multiplying them together. With velocity, we are one step closer to finding the force of the jump according to the equation shown. The variable d refers to the distance that the force is applied. From the earlier problem, we know that the distance is 0.298 meters. Therefore, the force required for this jump is 2,278.8 newtons.
Before we delve into the biomechanics of a pool jump, let's quickly review the components involved in movement in water and how they differ from movement on land. The main components involved are the density of water, drag force, propulsion or thrust, and buoyancy and gravity. From the picture, you can see how the different forces act on a body trying to move in water. Density is the main game changer. Because water is 832 times denser than air, a body trying to move in water has to displace a very high number of particles. Drag force is simply the force that acts opposite to the direction of motion, very similar to friction. The drag force of water is higher than that of air due to the higher density. Propulsion, or the thrust force, is the force needed to overcome this resistive force. Finally, buoyancy is the force that counteracts gravity to provide an upward lift to submerged or floating objects. While buoyancy will not be relevant to our calculations, drag force and thrust will be integral.
Considering the concepts just discussed, let's take a look at two different running performances produced by the same person, one on land and one in a pool. Comparing the two runs just from a qualitative standpoint, it is very clear to see that an identical motion in water is much more difficult to accomplish than its counterpart on land. Now we will analyze an athlete actually capable of completing this feat. Jerron Gilbert stands at an impressive 6 foot 5 inches, which is 1.9558 meters, and weighs a whopping 289 pounds or 131 kilograms. First, we calculated the amount of force needed for Gilbert to jump out of a dry 4-foot pool. Because of the height and weight change of the subject, the velocity and distance in the force equation also changed. First, to find the d, we use the same method as before with a femur length of 0.53 meters, because that is 27% of 1.9558 meters. To find the velocity, we again subtract the femur length from the height of the jump, still 4 feet, to find the change in distance of the center of gravity. Solve for time using the distance equation, then solve for velocity by multiplying acceleration and time. Using the velocity and time, we calculated the theoretical force of this jump to be 2,852.3 newtons. This is roughly 600 newtons greater than the previous athlete's jump. Completing this jump in water adds a drag force due to the water resistance. Therefore, the total force of the jump must equal the original thrust force plus the drag force of the water. The drag force equals 1/2 times the product of the density of the fluid, the cross-sectional area, the coefficient of drag, and the velocity squared. The thrust force is equivalent to the prior dry jump of the same 4-foot height. Setting two equations for momentum equal gives us a way to determine the force. We measured the time of the thrust to be about 0.2 seconds. The density of water is 998.2 kilogram per meter cubed. The cross-sectional area was determined by finding the average volume of a 6 foot 5 inch, 289 pound man and dividing by his height, which gave a value of 0.0679 meters squared. The coefficient of drag for a human in water is 0.45, and the mass of the athlete is 131 kilograms. With these known variables, we can solve the equation for velocity. Solving the quadratic equation for velocity gives 4.918 meters per second. Just for reference, the distance of the force is 0.3105 meters. Plugging the known velocity into the equation and summing the thrust force, drag force, the force of the jump is determined to be 3,221 newtons.
With all that said, let's take a look at our original athlete capable of completing a 4-foot box jump attempt to jump out of a pool. Clearly, the key word there was attempt, as he was not very close to landing outside of the pool. This implies that the drag force added by the density of the water must have been too great for his maximum thrust to overcome. So just how much force really is 3,200 newtons? Well, it's more than the biting force of a lion, which measures in at about 3,100 newtons. Still not impressed? That's fine, try it for yourself, or better yet, try it backwards like Keith Alloy.
Come on and